Hi, Carrie.
Reaction at low pH, so acidic conditions. And it's a project that really came together because we had sort of the right ideas, the right people, and the right equipment kind of all in the right place at the right time. So the motivation for this is that we want to do the oxygen evolution reaction. We want to catalyze that reaction. And the reason we want to do that is because it's one of the half reactions involved in this redox reaction called water splitting. So in this reaction, we take water and it requires energy, but we can split it into hydrogen and oxygen. And the hydrogen can be used as a fuel, and it can be used in a vehicle or a fuel cell or something like that. We'd like to get the energy to do this water splitting reaction from the sun. If we could do that, we would have a renewable energy source here, and we would have a pretty abundant feedstock with water that could be used to make a solar fuel. You're probably familiar with the idea that we can use this energy from the sun and solar panels to create electricity, but it's also nice to be able to take that energy from the sun and store it so it could be used during times when the sun is not shining at night, or at places that aren't very sunny on Earth. And also we could then store it and use it for like transportation needs, where that would be where fuels are really going to usually be used, no matter what other technological advances are made. So the type of device that would be used to convert solar energy and water into hydrogen fuel, we have kind of a cartoony picture here, but is a photoelectrochemical cell. And I sort of have some different colored boxes to kind of let you know that there's a lot of different components that have to come together to make this work. We need to have some type of material here in the middle that can absorb the photons from the sun and use that to create electron hole pairs that can then go to our anode and our cathode to do our two half reactions. So at the anode, we would do our oxygen evolution reaction. So that's this top one here, where we're going to take water and we're going to convert it into oxygen, 4 protons and 4 electrons. And then those electrons and those protons can come over here to the cathode, and we can do the hydrogen evolution reaction where we form hydrogen. And so both of these half reactions are going to require a catalyst. And so there's a lot of work trying to develop the light absorbing materials and the catalyst for both the half reactions. And so even once all those are developed, we still need to try to integrate them into a device that would work and be optimized. There's some other components as well that I didn't really highlight here. But in my lab, we're mostly focused on just wanting to look at this, this oxygen evolution reaction part and not worry too much about the other stuff. So we're just trying to come up with some good catalysts that can do this oxygen evolution reaction. And one of the reasons, so we're just taking that one box here, we're going to focus on that. One of the reasons for focusing on this is that the oxygen evolution reaction is generally considered to be a bottleneck in this process. It's kind of kinetically challenging because there's a lot of electrons involved, and you have to form an oxygen-oxygen double bond. So there's a lot going on. So you need some good catalysts for that. So what would make a good catalyst? We would want them to be active. We want them to be able to do this oxygen evolution reaction, and hopefully at low potentials, as low as possible. We'd like the materials that are used to be inexpensive and earth abundant so that we can scale up the technology. And we need the catalyst to be stable under the conditions that we're doing the reaction. So the photoelectrochemical cell that I showed on the last slide, it's generally considered that those components for the photoelectrochemical cell are optimized for acidic conditions. Unfortunately, for this half reaction, under acidic conditions, the catalysts that work best are iridium and ruthenium based materials, often iridium and ruthenium oxide materials. And so as we're going to see on the next slide, iridium and ruthenium are expensive, and there's not a lot of it on Earth. And so if we can get away from using so much of that, that would be great. And at higher pH and neutral or basic conditions, we're able to use first row transition metals to do this catalysis. So they can be used as the electrocatalyst in that case. For instance, under basic conditions, metal oxides or metal oxyhydroxides can be used. However, these first row transition metals are not very stable under acidic conditions. So we'd like to somehow try to get around some of these problems. And I didn't see my electrochemical cell here because it was behind all of the black boxes from Zoom here. But in order to just sort of focus on the oxygen evolution reaction, instead of using a photoelectrochemical cell, we're just going to use an electrochemical cell. So we're not going to have, I'm not going to use solar energy, we're just going to use electricity, and we're just going to try to test some different catalyst materials. Okay, so I said we wanted to get away from using iridium and ruthenium. So on this slide, I'm showing you some information about the abundance of some different elements in the Earth's crust, and it's comparing them to the abundance of silicon in the Earth's crust. But what we can see is as we're going across with atomic number here, is that iridium and ruthenium are about as bad as it gets. So if we want to scale up using photoelectrochemical cells to make solar fuels, we probably need to get away from using iridium and ruthenium, or at least not use as much. So there's a lot of technology, a lot of people trying to maybe not get rid of using iridium and ruthenium as catalysts, but try to not use as much. But there's other people who are trying to use first row transition metals because they're cheaper, and we can see they're more abundant here. But then we run into that problem that if we want to use acidic conditions, we need to come up with some way to stabilize them because they will dissolve under acidic conditions. So that's kind of the challenge here. We either need to not use as much iridium or ruthenium, or we need to get away from using it, but maybe try to stabilize some other metals that we have seen can be good catalysts under basic conditions. So they have catalytic activity towards oxygen evolution, but they're just not stable. Okay, so a couple of years ago, in inorganic chemistry, Ray Shack's group from Penn State, they published this paper where they looked at a new class of materials that could be used as oxygen evolution reaction catalysts. So I told you a lot of people have been using oxides, metal oxides, and things like that. But what they decided to do is kind of go like use a metallurgy kind of approach and melt different metals together and make this group class of materials called intermetallics. And I'll tell you more about what they are in a little bit, but you can kind of picture as they're a metallic material that contains more than one type of metal. Okay, and so their strategy was to combine an oxygen evolution reaction metal that's abundant, like a first row transition metal, with something that can stabilize it. And so the materials they looked at, they took a first row transition metal like nickel, cobalt, or iron, and they tried to stabilize it by incorporating tantalum into their materials. And so they used a 2-to-1 ratio of the catalytically active metal to the stabilizing metal. And most of the study is about nickel 2 tantalum, but they also made a cobalt 2 tantalum and an iron 2 tantalum. And these materials were more stable than the first row transition metal alone. And there's a lot of data here, but I mostly just wanted to draw your attention to right here. This is actually the electrode that they made. So they melted the metals together, which I'll tell you about how that works in a minute. And then they extruded it, and they kind of have a rod here that's 3 centimeters long. So they can actually make a whole electrode that can then be used as both an electrode and a catalyst. And so I thought this was really interesting because I've been interested in trying to do OER at low pH. But I also found out that we had the equipment in my department to make these intermetallic materials. Specifically, one of our emeritus physics professors has an arc melter that can be used to melt these metals together, and she makes some magnetic materials this way. And so we decided we'd kind of join forces and try to kind of riff on this and see what we could do. So what are these intermetallic materials? So intermetallic materials are similar to alloys, but the difference is that, at least the way some people define them, is that they need to have at least a partially ordered crystal structure, and that crystal structure should be different from the constituent elements. So if we're bringing together nickel and tantalum, they each have their own structure, but when we put them together, they're going to adopt a new structure. And so that would make it an intermetallic. This would be different than like an alloy where maybe you have nickel and it has a certain structure and you just replace a few of the tantalum or nickel atoms with tantalum atoms or some other, just sort of like replacing a few, but keeping the overall structure. And It turns out that these intermetallics have been widely explored in pretty similar applications to what we're interested in, but there's really not very many examples being used for oxygen evolution reaction beyond the example I just showed you from the Ray Shack's group from Penn State. And there's a handful of other ones where but they contain like platinum and palladium. So there's not very many other examples that only contain that don't contain precious metals, I guess. So here's a fairly recent, I guess it's a 2019 review article here, where they talk about all different kinds of intermetallic compounds or materials that have been used in electrochemical energy conversion. So for like CO2 reduction, things that are very similar to water splitting. But like I said, there's only a handful of examples for oxygen evolution reaction catalysis. There are some benefits to using intermetallic materials. I guess the first one is that I didn't really mention here is they're easy to make. But also there's lots of compositions to explore. We can look at binary mixtures with 2 metals, or we could incorporate a 3rd metal or 4 metals. So there's lots of composition space to explore. The second is that these materials are metallic, so they're conductive. At high pH, when people have used metal oxides as catalysts, those are not conductive. And so you have to use a separate electrode, and you have to make sure that you don't use too much of the oxide, so it's too thick and it doesn't conduct electricity. So there's other concerns there. So it's nice to use a conductive material. And then since when we make the intermetallics, they should have a separate structure from the individual metals, we have these new structural environments that may impose new properties, like new electronic properties that may be beneficial for catalysis. So with these things in mind, we can go back to which metals are earth abundant. And we can see that in the example that we saw with the tantalum, the nickel and the tantalum, that we have our first row transition metal, and we're incorporating tantalum, which is a lot more earth abundant than iridium and ruthenium, several orders of magnitude, in fact. And so that's one step into trying to make these first row transition metal materials acid stable and more cheaper and more abundant. So they were more acid stable. And so we're interested in maybe looking at some different compositions of first row transition metals with tantalum. But then we also thought, could we replace tantalum with even more earth abundant stabilizing metal? And we kind of had our eye here on titanium. And so we're going to see on the next slide the compositions that we decided to make. But we looked at some first row transition metals with tantalum, but then also it tried to incorporate titanium to stabilize our first row transition metals. So we have made some materials that are nickel based, and we've made some that are cobalt based. We have made all these materials, but we have not really studied the cobalt ones yet. So I'm going to mostly focus on the nickel catalysts going forward. We prepared 2 materials that had been prepared before, just nickel, to see how, without the stabilizing metal, how that behaved. And then we also produced the nickel to tantalum material that had been reported by the Shack group before in that inorganic chemistry paper. We also looked at a second nickel tantalum material. We combined them in a 3-to-1 mole ratio to make nickel 3 tantalum to see if that would change the stability and or the activity of the catalyst. And then we looked at some titanium, included some titanium and some materials to make nickel 3 titanium and a 1-to-1 nickel titanium material here. And so I'm going to tell you about those. So you can see we have some, maybe it looks like a little random as far as the mole ratios that we picked, but we at least tried to be somewhat guided by the phase diagram for these materials. So this is the phase diagram for nickel and titanium. And so we were hoping with the 1-to-1 mixture that we'd be able to get that pure phase of nickel titanium. And then also we were hoping to get the nickel 3 titanium 1 material as well. Okay, and so those are the reason we kind of chose these things that are a little bit different than these ratios up here. So these are the color coding that we're going to use going forward, just to kind of keep track of what's what here. So that's why they're colored here. So now I'm going to tell you a little bit about how we made these and how we studied them. So the way that we prepare these is I told you that we need to melt these metals together, and we do this using an arc melter, which is basically a big power supply. And then up here at the top is where we end up melting these together. So if we zoom in a little bit, There is a globe in here, and inside there is a copper hearth, which is taken out here so you can see. And at the top, there's a handle, and then there's an anode sticking down. So here I am holding it outside of that globe. And it's got a lanthanated tungsten anode, which is also called a stinger. And we're gonna then put our metal. We're gonna weigh out our metals in the desired mole ratios, and we aim for about a gram of total metal to make about a gram of our intermetallic material. And you put that in the hearth here. That can be a piece of a wire or a foil or a piece of the metal. And you put those pieces close together, and you put the hearth down here, and you put the stinger in. And when you turn on the power supply, you have to put, I didn't put this on the picture, but you have to put a piece of like a welding shield to make sure that you don't look directly at it. And basically, there's going to be an arc between the stinger and the hearth. And if you position that to go through the metals, they'll melt together. And so we do this several times, at least 3 times, and to make sure that they're thoroughly melted together. And what we get are hopefully our intermetallic materials, where you can see we're kind of zoomed in here. Here it is. There's going to be kind of a flat side. Here it is on the bottom. Here it is on the top. A flat side that has been formed when it's like against the hearth, and then it's kind of looks just like a blob on the top here. So those are what we made. And so we made each of those intermetallic materials, and then we wanted to characterize them and then make them into electrodes and test them electrochemically. Let's see, was there something else I was gonna say here? I don't think so. Okay. Oh, so anyway, so I didn't really show this, but like I said, you kind of have to put a welding, like you have to look through welding glass, so you can't really see what you're doing. And I haven't managed to like master this yet, but my students are very good at sort of working blind and getting this to work. So we took these little blobs of intermetallic materials that we made, and we at least tried to get some initial characterization using powder X-ray diffraction. And so we characterized all of our intermetallic materials this way. As I just said, it's powder X-ray diffraction. So you think that your sample would be a powder, but it turns out these materials were too hard to break into a powder once we incorporated either titanium or tantalum. And so we decided just to sort of take the flat side of that intermetallic material that we had arc melted and try to get the diffraction off of that. So here's a picture inside of our XRD instrument, where we have our X-ray tube coming in, and the X-rays will come from the left through some optics. And then in the middle here, we have mounted our intermetallic materials with the flat side up. And if anyone has a better idea of how to mount these, please let me know. But we just couldn't figure out what to do. So we mounted them in Play-Doh, which really didn't have too much of a XRD background. And then the X-rays come off of the surface and are detected over here in the detector. And these angles will change, and we can see we get an XRD pattern here. And there are more sort of sophisticated ways to analyze these, but at this point you can kind of think about it like a fingerprint, where we want to see if our pattern matches the expected pattern of the material we hoped we had made. So here's the nickel titanium pattern that we got in blue here, compared to one from the crystallography open database right here. So they look like they match, at least to the first degree here. We haven't got this all quite figured out yet, but we can see here with the nickel 3 titanium, again, it looks like it has the peaks that are expected. Some of the intensity may be different because we don't have a powder, since we're looking at a surface instead. With the nickel 2 tantalum, we see the expected peaks, and it looks like our nickel 3 tantalum might be a mixture of a couple of different phases. So at the very least, they look like they're crystalline in nature, and regardless of exactly what they are, we wanted to see how they performed for oxygen evolution reaction electrocatalysis. So we needed to take these little blobs. So in the Shack group, they had made like a rod that they could use as an electrode, but we don't have that capability of doing the extrusion and making it into a rod. So what we did is we needed to construct our electrodes here. So down here is our piece of our intermetallic, our little blob there, and we had the flat end here, and we attached it to a copper wire using conductive silver paint, and then and epoxy. And then we housed it in plastic, meaning that we took a pipette tip and we cut the end of it off, and we were able to make our electrode in there. And then to do our electrochemical testing, we took our electrode right here, and we set up this 3-electrode electrochemical cell. All of our measurements were performed using a Pine Wave Now potentiostat. We have a silver chloride reference electrode, a platinum mesh counter electrode. Here's that electrode. The working electrode has the intermetallic catalyst material there. And our electrolyte was very acidic. It's 0.5 molar sulfuric acid. So that's what we use for our conditions for our test, to test our electrocatalysts to see if they're, remember, we want to see if they're active, and we want to see if they're stable. And we know that they're pretty earth abundant. So the first thing we looked at was the linear sweep voltammetry. And so in this kind of electrochemical experiment, what you do is you scan, in this case, we scanned to more oxidizing or positive potentials at a constant rate. We did this at 10 millivolts per second, and we measure the current that happens. And so all of these materials, so we have our nickel, we have our nickel tantalum materials, and we have our nickel titanium materials. All of them show a catalytic wave in the region that we scan. So we're scanning here and there's no current, and then we get to a certain, let's just look at the nickel here. We get to a certain potential and we start to see this rapid increase in current. And that means that we're doing oxygen evolution, or at least we think that that means that we're doing the oxygen evolution reaction. We need to actually detect oxygen to make sure that that's what was happening. But this is a characteristic catalytic wave that these all show. And what we can see is basically, if this catalytic wave starts at a lower potential, like it does here for nickel, and then next nickel 3 titanium, that means that it's more active. Okay, so I've shown an arrow here, and this is approximately the earliest, the lowest potential that thermodynamically we could start to see a catalytic wave. And so any extra above that is called the overpotential. So we would say nickel has the lowest overpotential, and then nickel 3 titanium, and then sort of these two materials, or sorry, then the nickel 3 tantalum, and then the 1-to-1 nickel titanium, and then the one that was reported in the previous paper, the nickel 2 tantalum. So what we can kind of say here is that the compositions that have a higher proportion of nickel are more active, but remember, we expect they may not be very stable. But I would say that one thing that we could say is that all the new materials that we've made are pretty promising compared to the previously reported green one here, the nickel 2 tantalum, which was not a great catalyst, but was at least like a respectable catalyst. So all of ours are at least as respectable, or if not a little bit more. Okay, so this is showing us about the activity. And so we can say what's going on as far as which ones might be good at catalyzing this reaction, but we also want to consider their stability. So then we did an experiment called chronopotentiometry. And so in this type of experiment, what we did is we held the current constant. So we measured how much of our catalyst was exposed at the bottom of our electrode, and we were able to then take that and account for what's called a current density. So we held our current density at 10 milliamps per centimeter squared for 24 hours, and we measured the potential over that 24 hours. And basically, if a material has a lower potential, it means it's a better catalyst. So again, we see the 3-to-1 nickel titanium and the 3-to-1 nickel tantalum are the best. And then we have our nickel 2 tantalum, and then maybe the 1-to-1 ratio here. But not very, the measured potentials of all of them did not change very much during the 24 hours. I think that means that basically you still have a catalyst there and it's still working. So the surface isn't becoming really different, and there's still some catalyst there to do the reaction. I didn't show the curve for nickel because it was really, really noisy. I think because it's actually not stable, it's actually dissolving during the reaction. And so when we look at this, some of our after the reaction ran for 24 hours, some of the electrolytes are actually visibly colored after the reaction. So specifically, the nickel electrode is a solution that was in the nickel electrode for 24 hours during the reaction is green. So it looks like we've lost a significant amount of nickel. And then also the 3-to-1 nickel titanium is a yellow color here. And so it just based on looking at these, we can kind of guess that at least maybe this one and this one are not very stable because we're actually dissolving the electrode during 24 hours of operation. And so we wanted to quantify how much of the metals was lost into this solution over this 24-hour reaction period. And so we performed ICP OES. So this is inductively coupled plasma optical emission spectroscopy. So here's our instrument right here. And basically this is going to, it's basically a form of elemental analysis where we're going to find out how much of the metals we have. So you aspirate or suck up your solution into the instrument, and it has a nebulizer that creates a mist, and then it goes into a very hot plasma, which turns the sample into its atoms, and the atoms are excited, and then they each give off their characteristic wavelengths, and you can detect those and say how much of each thing you have. So we quantified the amount of nickel and titanium in our materials. We didn't look at tantalum because we didn't have the standards to run for that particular one yet. And so we wanted to quantify for each of these how much of those metals were lost during the electrocatalysis for 24 hours. And so this is what that looks like. We have each of our materials here. All of our, maybe I should have presented this a different way, but each of our electrodes had a mass of about 1 gram. And then you can see how many milligrams of nickel and titanium were lost over the 24 hours. So the nickel electrode that was didn't have any stabilizing metal in it lost almost 100 milligrams of nickel over that 24-hour period of acidic OER reaction. And so that's why we have this green color that we can see. We can see that the other one that was discolored, the yellow one, the nickel-3 titanium, also lost not quite as much, but it lost a lot of nickel, and it also lost some titanium here. And so the other ones, though, the 2-to-1 nickel tantalum that had been reported before, as well as the nickel-3 tantalum and the 1-to-1 nickel titanium, they're a lot more stable over the other 2 materials. So in each of these cases, we're losing a little bit of nickel and titanium, but it's less than 1 milligram for each of these. And so that's nice because we can say that the nickel-3 tantalum was actually more active than the nickel-2 tantalum, so that's promising. And then this new material where we've incorporated a more earth-abundant stabilizing metal, the titanium versus the tantalum, also seems to be pretty stable. So I haven't talked very long here, but that's kind of our story here. So our conclusions here are that we had this strategy that was building on previously reported research, where we wanted to combine an OER active abundant metal, like a first row transition metal, with an acid stable metal. And we were able to find a new composition of nickel and tantalum that is more active than the previously reported one and as stable. And then also we were able to incorporate a new stabilizing metal here that was able to behave almost as well as at least the previously reported one. And so as far as where we're going to go from here, we have all these cobalt electrodes that we still need to look at. I'm not exactly sure what's going on with some of these compositions. I think some of them were just sort of things that got made, but we have them. So we'd like to test those and maybe strategically plan some more cobalt compositions here. So we'd like to look at that. We may also test some additional molar ratios of nickel and titanium or nickel and tantalum to see if there's anything that can strike a balance between activity and stability. And then, as I mentioned, one of the benefits of these materials is that we can explore adding more metals. So we could look at ternary compositions of possibly 3 metals. So for under basic conditions, where I said that metal oxides were good catalysts, nickel oxide or nickel oxyhydroxide has been found to be a good catalyst, but if you incorporate a little bit of iron, it's an even better catalyst. So having a second metal really increases the catalytic activity. So there's no reason to think that that might not be the case here, where we might be able to develop or stumble upon a better catalyst. So that's kind of where we're going, and we haven't gotten too far into this, but I think it looks promising, and I'm pretty excited about it. So I'd like to thank the people that have helped me with this. Dunya is the grad student who made all of these nickel electrodes and tested them electrochemically. Farinac made the cobalt ones that we still need to test. And then Dr. Hill is the one who taught us how to arc melt. And here we are in front of our powder X-ray. This is Danya right here. So we're excited to have that, even though we're still learning. We have an SF grant that we got that from. So we're excited about that, but hopefully we'll learn what to do besides mount everything in Play-Doh. So I appreciate you guys listening to me. I know it's towards the end of the semester and we're all done being on Zoom. But if you have any questions, or ideas or thoughts, I'd be happy to hear what you have to say.
All right, so what questions do we have for Dr. Shaner?
I actually had some ideas and thoughts.
Okay.
While I was working at MDI, I used some acoustic levitation to like hold a sample. So like if you're looking for something to hold, like while you're doing like PXRD, that might work well. I don't know.
Yeah, I know. I watched those videos when you told me about that and I still don't understand it, but it looks crazy. It's good to see you, Jess.
It's good to see you too.
Yeah.
I have a question. So you're talking about all these different materials, and some are active and some not so active. Do you have any idea of like the mechanism of why some things would work and some things wouldn't?
Not super great idea. So I think there are certain metals that, based on their electronic properties, are more likely to be active. But I think also, like, if you can get them in sort of, sometimes people think if you can get them in distorted geometries, maybe that might promote catalysis as well. So I think that there is like some room to play here where you can like mess with the structure as well. Maybe not predict it, but you might be able to maybe someone could. I can't predict it at this point. But I do think like nickel is often shown to be one of the most active ones. So I assume that there's, some basis just about its electronic properties. You could see it had like kind of it had an oxidation wave before it took off in its catalytic wave. So sometimes they have to go to higher oxidation states before they can then become catalytically active. So I think there's something about the electronics, but I think you can also play with like the bonded structure around it.
I have another question.
Yeah.
So you're focusing on first row transition metals, but there are some second row transition metals that are pretty earth abundant.
That's true.
And they can tend to be more stable than the first row. So have you thought about doing any second rows?
I have not yet, just because I haven't, but yeah, I'm not opposed to that. I think, like I said, if you can get away from iridium and ruthenium, I think you're basically like doing great. So I think there's like a huge, room to grow there and to improve. Yeah, it's just sort of shorthand for cheap and abundant first row transition metals. Maybe we're leaving out the second row ones and they're being, neglected. So
Yeah, we wouldn't want to do that.
all the elements are important.
All right, do we have any other questions from our audience? All right, well, if there are no more questions, let's thank our speaker, Dr. Shaner from Southeast Missouri State, for giving a wonderful talk. I think we all learned something today about electrocatalysts.
Hopefully. Yeah, thanks for everybody for coming.
Thank you, everybody. Oh, I better do an emoji here. There I go. See?
Great. Everyone have a good weekend.
All right. Bye-bye, everybody.